The sky was once a perfect crystal dome centered on our world. This video explores the 25 discoveries that shattered that illusion forever. You will witness the complete transformation of our cosmic identity, from the center of everything to a fleeting speck in a vast and evolving universe. We will uncover how a simple mathematical idea first set the stars in motion, and why most of the cosmos is made of something we cannot even see. What does it feel like to have your entire reality rewritten? Nicolaus Copernicus saw a problem in the heavens, a mathematical clumsiness that had troubled astronomers for centuries. The old Earth-centered model, with its complex loops and circles in the sky, felt forced and artificial. In his quiet study, surrounded by charts, he found a simpler, more beautiful solution. What if the sun was the true center? He proposed that our world is not a stationary stage but a traveler, spinning on its axis and circling a central star. This single idea, published in the year 1543, did more than rearrange the planets. It struck at the very heart of human self-importance. For over 1,000 years, religious and philosophical doctrine had placed our world at the center of God's universe. Now, we were suddenly demoted, becoming just another rock in motion around a cosmic fire. Copernicus himself saw the elegance in his new design, asking who would place the lamp of a beautiful temple anywhere but the center, where it could light up everything at once. This was a terrifying freedom. The solid ground was no longer solid but a ship sailing an endless sea. How would you have slept knowing you were hurtling through the void? This philosophical earthquake was only the first tremor. The next discovery would prove that even our brilliant sun was not the unique beacon we believed it to be. Galileo's hands trembled not from the night's chill but from the sight before his eyes. Through his modest spyglass, the moon was transformed. It was not a smooth, perfect orb as the ancient philosophers had declared, but a rugged landscape of mountains and valleys, a world much like our own. This single observation began to dismantle a fundamental belief that the heavens were a realm of immutable perfection, separate and superior to the flawed Earth. But he saw more. Turning his telescope to Jupiter, he found 4 tiny stars that steadfastly accompanied the planet, night after night, changing their positions around it. They were moons, a miniature solar system with Jupiter at its center. Here was undeniable proof that not every celestial body circled the Earth. The final, most elegant blow came from Venus. He watched it pass through a full set of phases, from a thin crescent to a full disk, a cycle that only made sense if Venus was traveling around the Sun, not us. These were not philosophical arguments, they were physical facts. He published these revelations in a small book he called The Starry Messenger, and the message was clear. The old universe was gone. This evidence, however, came with a terrible price. It directly challenged the authority of the Church, which had woven the Earth-centered model into its very doctrine. Galileo was summoned to Rome, forced to recount his findings, and spent his final years under house arrest, a prisoner for telling a truth the world was not ready to hear. Yet his legacy was secure. He had given humanity new eyes, proving that the cosmos could be understood not by ancient text or pure thought alone, but by looking, by testing, by evidence. So much had been hiding just beyond the limits of our vision. What else was waiting to be seen? The next great mind would not need a telescope, only a pen and paper, to discover the invisible force that choreographed this entire cosmic dance. Isaac Newton sat in a quiet garden, and where others saw only an apple falling, he saw an invisible thread connecting it to the moon itself. That simple, everyday event sparked a revelation of cosmic unity. The very same force that drew the fruit earthward was the one that kept our satellite gracefully circling our world, and our entire planet tethered to the sun. He had uncovered a single rule that governed motion both on Earth and in the heavens, a law of universal gravitation. In his great work, the Principia Mathematica, published in 1687, he presented this idea with mathematical precision. He proposed that every single object in the cosmos, from the smallest pebble to the largest star, pulls on every other object. The strength of that pull depends on their masses, and crucially, it weakens with the square of the distance between them. This means if you double the distance, the gravitational force becomes not half, but only 1/4 as strong. This single equation was a key that unlocked the universe. Suddenly, the chaotic dance of the cosmos made sense. The predictable return of comets, the precise timing of eclipses, the slight wobbles in planetary orbits, all of it could be calculated and predicted using Newton's laws. He gave humanity a profound gift, the vision of a clockwork universe. The cosmos was not a realm of capricious gods, but a magnificent machine operating under knowable mathematical laws. For centuries, this view of a predictable, deterministic cosmos reigned supreme. It seemed that with enough knowledge and calculation, the entire future of the universe could, in theory, be foretold. But was this cosmic clockwork truly all there was? Could such elegant laws truly explain the sheer scale and structure of everything we see when we look up? The next leap in understanding would shatter this comfortable view, revealing that our entire Milky Way, with its hundreds of billions of stars, was merely a single flickering candle in an unimaginably vast and dark cathedral of space. For centuries, those faint, fuzzy smudges in the night sky were simply cosmic clouds, mysterious but local features of our own starry Milky Way. They were thought to be mere swirls of gas and dust, part of our own celestial neighborhood. But one astronomer, Edwin Hubble, aimed the most powerful telescope of his time, the 100-inch Hooker telescope, at the most prominent of these patches, the Andromeda Nebula. He was not looking for clouds, he was searching for a specific kind of stellar lighthouse, a Cepheid variable star. These are special stars that pulse with a regular rhythm, growing brighter and dimmer over a set period. The true magic of these stars is that their pulse rate reveals their true brilliance. By measuring how long its cycle of brightening and dimming took, Hubble could determine the star's intrinsic power. Then, by comparing that known power to how faint it actually appeared in his telescope, he could perform a simple calculation, like figuring out how far away a 100-watt light bulb is by how dim it looks. The answer he got was staggering. The Cepheid star in Andromeda was so incredibly distant that it could not possibly reside within our own galaxy. The Andromeda Nebula was not a nebula at all. It was an entire island universe, a colossal city of stars millions of light years away, completely separate from our own. In a single moment, the known universe exploded in size. Our Milky Way, which we had thought was the entirety of creation, was suddenly reduced to a single neighborhood in a cosmos teeming with billions of other galaxies. We had gone from being the only city on the map to realizing we lived in one humble town in an endless, sprawling country. But Hubble's next discovery would be even more profound. He would soon realize that these distant island universes were not merely far away. They were all racing away from us and from each other at unbelievable speeds. Hubble had just thrown open the doors to a universe filled with galaxies, but the cosmos had one more, even deeper secret to reveal. As he measured the faint light from these distant island universes, he noticed something strange in their colors. The light from almost every galaxy was stretched, shifted toward the red end of the spectrum. This redshift was a cosmic speedometer, and it told a shocking story. The galaxies were not just drifting, they were racing away from us, and the farther away a galaxy was, the faster it was receding. This simple, direct relationship, now called Hubble's law, pointed to a single, staggering truth. The entire universe, the very fabric of space itself, is expanding. Think of the universe as a loaf of raisin bread rising in the oven. The dough represents space and the raisins are the galaxies. As the dough expands, every raisin moves away from every other raisin. From any single raisin's perspective, all the others are fleeing, and the more distant raisins appear to move away faster because there is more expanding dough between them. This was not about galaxies flying through space, but about space itself stretching, carrying the galaxies along for the ride. This single observation shattered the ancient belief in a static, eternal cosmos. Even Albert Einstein had been so convinced of a stable universe that he inserted a fudge factor into his equations to keep it still. Hubble's evidence forced him to call this his greatest blunder. The universe was not permanent and unchanging. It had a history. It was born. The logical conclusion of this cosmic expansion, if you run the film of time backward, is that everything we see, every galaxy, every star, every atom, was once compressed into an unimaginably hot, dense point. This was the first solid observational evidence for what we now call the Big Bang Theory. Our home was no longer just a place in space, but a moment in time, part of a grand cosmic story that began nearly 14 billion years ago. We live inside an event, an unfolding narrative of creation itself. If the universe began in a fiery genesis, where is the evidence? Where is the heat from that initial blast? The answer would come from the most unlikely of places, a faint and forgotten hiss that will be discovered completely by accident. Two young radio astronomers were simply trying to eliminate a persistent, maddening noise. Arno Penzias and Robert Wilson at Bell Labs were using a sensitive horn antenna, but their work was plagued by a faint, steady hiss that came from every direction in the sky, day and night. They scrubbed the entire apparatus, even evicting a pair of pigeons and carefully cleaning up their droppings, convinced the signal was some kind of earthly interference. But the hiss remained, an unshakable whisper from the cosmos itself. This annoying background noise, which they could not explain or remove, was in fact the most important signal ever detected. It was the cooled and faded afterglow of the Big Bang's initial fireball, the cosmic microwave background radiation. This was the smoking gun that cosmology had been searching for. Theorists had predicted that if the universe began in a hot, dense state, the entire sky should be filled with a faint remnant of that primordial energy, cooled by the expansion of the universe over billions of years to just a few degrees above absolute zero. Penzias and Wilson had found it. That faint hiss was the oldest light in the universe, a snapshot from a time when the cosmos was just 380,000 years old. Before that moment, the universe was a searing, opaque fog of plasma, too hot for light to travel freely. As it expanded and cooled, the first atoms formed, and the universe suddenly became transparent, releasing that light on a journey that would end 13.8 billion years later in a radio antenna in New Jersey. That light has been traveling ever since, stretched by the expanding universe from visible heat into the microwave whisper they detected. It paints a picture of a universe that was once incredibly hot and dense, confirming its explosive origin. This discovery cemented the Big Bang as the foundation of modern cosmology and gave scientists a perfect fossil, a time capsule from the universe's infancy. By studying the tiny, tiny variations in the temperature of this background radiation, we can read the blueprint for all the structure we see today, the seeds from which galaxies and clusters would eventually grow. What other primordial secrets are written into this ancient, universal code? This relic radiation would soon point toward a mystery even more profound than the universe's birth, hinting at a hidden force shaping its ultimate fate. The faint hiss of the cosmic background radiation gave us a perfect baby picture of the universe, but when scientists looked closer, they saw a problem. The blueprint for the cosmos was strangely smooth. The infant universe was almost, but not quite, uniform, and the tiny ripples in its temperature were not quite strong enough to have seeded the vast cosmic structures, the galaxies and clusters we see today. Something else, something invisible, must have already been there, providing a gravitational scaffold for normal matter to cling to. That something had left its fingerprints decades earlier in the frantic motion of distant galaxies. In the 1930s, a brilliant and often overlooked astronomer named Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies. He calculated how much gravity the cluster should have based on all the stars and gas he could see. Then he measured how fast the individual galaxies were actually whizzing around. The numbers did not add up. The galaxies were moving so incredibly fast that the visible mass of the cluster was far too weak to hold them together. The entire cluster should have flown apart long ago. Zwicky concluded there had to be some other form of matter at work, a hidden source of gravity. He called it Dunkel Materie, dark matter. For decades, his idea was largely ignored, a curious anomaly. Then, in the 1970s, astronomer Vera Rubin provided the definitive proof, not from a distant cluster, but from the serene rotation of a single spiral galaxy. She meticulously mapped how fast stars orbit around the center of galaxies. According to Newton's laws, stars closer to the galactic center, where most of the visible mass is concentrated, should orbit very quickly. Stars far out on the edges, where there are fewer stars, should move much more slowly, just as Pluto orbits the Sun far more sluggishly than Mercury. But Rubin's data revealed something astonishing. Stars at the very outskirts of galaxies were orbiting just as fast as those near the center. It was as if the entire galaxy was embedded within an enormous, invisible sphere of matter, a vast halo whose gravity was whipping the outer stars around. This dark matter does not emit, absorb, or reflect any light. It is completely transparent, interacting with our world only through its gravitational pull. We cannot see it, but we can feel its immense weight holding the cosmos together. We now know this mysterious substance makes up about 27% of the universe, while all the planets, stars, and galaxies we can see account for less than 5%. This was a humbling revolution. We had been studying the universe thinking we could see its major components, only to discover we were like someone studying an ocean by looking only at the foam on the waves, completely missing the deep, dark water beneath. We live in a universe dominated by a ghost, a cosmic skeleton whose shape we can map only by its gravitational shadow. But the plot was about to twist even further. Just as we were coming to terms with the fact that most of the matter in the cosmos is invisible, we would be confronted with a discovery that most of the universe itself is not even made of matter at all. Just as we were coming to terms with the ghostly presence of dark matter, the cosmos delivered an even more baffling twist. In the late 1990s, two teams of astronomers were using distant supernovae as cosmic mile markers. These exploding stars, known as Type 1a, all explode with nearly the same intrinsic brightness. This makes them perfect standard candles, allowing scientists to measure vast cosmic distances with precision. By observing how dim these supernovae appeared, the teams could calculate exactly how far away they were, and by measuring their redshift, they could determine how much the universe had stretched since the light began its journey billions of years ago. Everyone expected to find that the expansion of the universe was slowing down, gradually braked by the collective gravitational pull of all the matter, both dark and visible, working to draw everything back together. The big question was whether there was enough matter to eventually reverse the expansion in a cataclysmic big crunch. The data, however, told a completely different story. The distant supernovae were fainter than they should have been. They were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Something was actively pushing galaxies apart, overwhelming the relentless pull of gravity itself. This mysterious, repulsive force was given a simple, profound name: dark energy. It appears to be a fundamental property of the vacuum of space itself. The more space expands, the more of this repulsive energy is created, leading to a runaway acceleration that grows stronger over time. We now calculate that this invisible engine of cosmic expansion makes up about 68% of all the energy in the universe. Dark matter comprises another 27%. This means that everything we can see and touch, every star, planet, and galaxy, accounts for less than 5% of reality. Our entire understanding of cosmic fate was turned inside out. The expected endgame, a fiery collapse back into a singularity, was replaced by a far more lonely and gradual finale, a heat death. In this future, the accelerating universe will stretch the space between galaxies until they are isolated islands, their stars burning out one by one, until all that remains is an ever-expanding, ever-cooling, and ultimately empty darkness. How can nothingness, the sheer emptiness of space, possess such a powerful, repulsive quality? This discovery forces us to confront the profound mystery that the vacuum of space is not truly empty, but seething with a hidden energy that is shaping the ultimate destiny of everything. Albert Einstein's mind ventured where no telescope could see. He realized that Isaac Newton's elegant force, while brilliantly describing the solar system, left a deeper mystery untouched. What was gravity, really? In 1915, Einstein published his theory of general relativity, and the answer was nothing short of magical. He proposed that gravity is not a mysterious force reaching across space, but a curvature, a warping of the very fabric of space and time itself. Mass and energy tell this fabric how to curve, and that curvature, in turn, tells objects how to move. Picture a taut rubber sheet. Place a heavy bowling ball in the center, and it creates a deep well. Now roll a marble nearby. It does not travel in a straight line, but curves inward, tracing an orbit around the heavier mass. The Sun does this to space-time, and Earth is simply following the curved path of that cosmic dimple. This single idea predicted phenomena that sounded like pure science fiction. Einstein calculated that the path of light itself would bend when passing near a massive object. During a solar eclipse in 1919, astronomers confirmed this, watching starlight curve around the darkened sun. His theory also revealed that time is not absolute. A clock ticks more slowly in a stronger gravitational field. This is not a theory. Your GPS would be useless without this correction, because the satellites in orbit experience time ever so slightly faster than receivers on the ground. General relativity perfectly explained the slight wobble in Mercury's orbit that had puzzled astronomers for generations. It gave us the mathematical language to describe the entire history of the cosmos, from the Big Bang to the existence of black holes. Space and time were no longer a passive stage, but dynamic, flexible actors in the cosmic play, capable of stretching, twisting, and waving. And if a star is massive enough, its final collapse could warp space-time so severely that it creates a pit from which not even light can escape. What could possibly form at the bottom of such an infinite curve? Einstein's equations contained a terrifying possibility. If enough mass were compressed into a small enough point, the fabric of space-time would curve into an bottomless pit, a region where gravity becomes so overwhelming that nothing, not even light, could ever climb back out. For decades, these black holes were seen as mere mathematical phantoms, too strange to be real. But the universe is not so timid. In 1964, astronomers detected a powerful source of X-rays in the constellation Cygnus, designated Cygnus X1. It was a cosmic beacon screaming its presence, but the visible star at that location seemed ordinary. The explanation was as violent as it was elegant. The X-rays were not coming from the star itself, but from an invisible companion, a black hole. Its immense gravity was tearing material from the star. pulling that gas into a swirling, superheated disk before it vanished forever across the event horizon, the point of no return. This was the first solid evidence that these monsters were not just theory, they were real. The discoveries grew even more profound. We now know that nearly every large galaxy, including our own Milky Way, harbors a supermassive black hole at its heart, an engine of unimaginable power with a mass millions or even billions of times that of our Sun. For the first time in 2019, we saw one. The Event Horizon Telescope, a global network of observatories acting as a single Earth-sized dish, captured the shadow of the colossal black hole at the center of the galaxy M87. The image showed a dark void, the event horizon itself, encircled by a brilliant, lopsided ring of light, the glow of matter being twisted and accelerated at the brink of oblivion. It was a perfect visualization of space-time warped to its absolute limit. Black holes are the ultimate expression of gravity's power, cosmic laboratories where the known laws of physics break down. What happens to all the information, all the matter that falls inside? Does it get crushed into a single point of infinite density? The answers to these questions may lie hidden behind that dark curtain, waiting to reveal a deeper truth about reality itself. If gravity can create such a perfect trap for light and time, what other, more subtle ripples could it send echoing across the cosmos? The first 3 minutes of the universe set the stage for everything to come. In that initial, unimaginable heat, the cosmos was a searing broth of fundamental particles, a chaos too intense for even atomic nuclei to hold together. But as space ballooned outward, it cooled at a frantic pace. Within those first critical minutes, a narrow window opened. Protons and neutrons, now able to grab onto one another, began to fuse. This frantic, universal alchemy is known as Big Bang Nucleosynthesis, and it lasted for only about 17 minutes before the expanding universe cooled too much for fusion to continue. In that fleeting moment, the recipe for the cosmos was written. This process forged nearly all the hydrogen that fills the universe today, along with almost a quarter of its mass as helium and a tiny, trace sprinkling of lithium. In the 1940s, physicist George Gamow and his team calculated what the abundances of these light elements should be, based solely on the known laws of physics and the conditions of the early universe. Decades later, when astronomers pointed their telescopes at the most ancient, pristine stars and clouds of primordial gas, they found a perfect match. The oldest things we can observe contain exactly the amounts of hydrogen and helium that the theory predicted. This is not a rough estimate, it is a spectacularly precise confirmation. That 17-minute burst of creation left a chemical fingerprint on the entire cosmos, a relic we can still measure today. It tells us that the entire universe was once a single, unified nuclear furnace. But this first act of creation only gave us the lightest elements, the simplest building blocks. It left a profound question hanging in the cosmic silence. Where did the rest of the periodic table come from? Where did the carbon for our cells, the oxygen we breathe, and the iron in our blood originate? The answer would not be found in the beginning of everything, but in the spectacular deaths of the first stars. The universe was left with only the lightest elements, a cosmic canvas barely touched. The recipe for everything else, the carbon, the oxygen, the iron, was a mystery locked inside the stars themselves. In the 1950s, a team of visionary scientists, including Fred Hoyle and Margaret Burbidge, cracked this stellar code. They realized that stars are not just distant lights, they are immense nuclear furnaces, cosmic forges where the elements of life are hammered into existence. A star's life is a constant battle against the crushing force of its own gravity, and its weapon is nuclear fusion. For most of its life, a star like our Sun fuses hydrogen into helium in its core, releasing the energy that makes it shine. But when the hydrogen fuel begins to run out, the core contracts. heating up until it becomes hot enough to start fusing helium into carbon. In more massive stars, this process continues in a desperate, layered struggle, creating ever heavier elements like oxygen, neon, and silicon, building up like the layers of an onion all the way to iron. But iron is a dead end. Fusing iron does not release energy, it consumes it. The star's energy production suddenly halts, and gravity, which has been held at bay for millions of years, wins in an instant. The core collapses catastrophically, and the star explodes in a supernova, a blast of unimaginable violence. For a few brief weeks, a single dying star can outshine an entire galaxy. In that incredible inferno, in the frantic rush of neutrons, every element heavier than iron is forged. Gold, silver, uranium, all the richness of the periodic table is created in this final, glorious stellar death. The explosion then hurls this newly forged material far out into space, enriching vast clouds of gas and dust. Fred Hoyle captured the profound consequence of this when he said, "We are all made of star stuff." The calcium in your bones, the iron in your blood, the oxygen you breathe, every atom in your body except for the primordial hydrogen was once inside the core of a massive star that lived and died long before our sun was even born. Our solar system formed from the recycled debris of such stellar explosions, a cosmic inheritance that connects us physically to the grand cycles of the galaxy. We are not just living in the universe is living in us. This breathtaking cycle of stellar life and death provided the raw materials for planets and life. But how did those raw materials ever clump together to form anything as complex as a galaxy, let alone a world? The answer lies in the faintest of echoes from the universe's very first moments. The Big Bang Theory gave us a cosmic genesis, but it left behind a few troubling mysteries. Why is the temperature of the universe, measured from one side of the sky to the other, so perfectly uniform? Distant regions should never have had time to exchange heat, to balance themselves out, unless something connected them in the very beginning. And why is the fabric of space itself so remarkably flat, rather than dramatically curved? In 1980, a young physicist named Alan Guth found an elegant solution to these puzzles, a concept he called cosmic inflation. He proposed that in the first fleeting fraction of a second, a tiny sliver of time like 10 to the negative 36 seconds, the newborn universe underwent a staggering growth spurt. It expanded exponentially, doubling in size again and again, faster than the speed of light. This was not matter moving through space, but space itself stretching at an unbelievable rate. In that blink of an eye, a region smaller than a single proton inflated to a size larger than our entire observable universe today. This violent smoothing ironed out any wrinkles, making the cosmos uniform and flattening its geometry, just as inflating a balloon makes its surface appear flatter and smoother. But inflation did more than just tidy up the cosmos. It also planted the seeds for all future structure. At the quantum scale, empty space is never truly still. It is a seething foam of virtual particles constantly flickering in and out of existence. During inflation, these tiny quantum fluctuations were suddenly stretched to colossal proportions. The microscopic hills and valleys in the fabric of space were magnified into vast regions of slightly higher and lower density. These minute differences in density became the gravitational seeds around which all the matter from the Big Bang would eventually gather. The slightly denser patches pulled in more dark matter and gas, eventually growing over billions of years into the galaxies and colossal clusters we see today. The faint temperature variations we see in the cosmic microwave background, that ancient baby picture of the universe, are the direct imprint of these stretched quantum ripples. While we search for more direct evidence, such as primordial gravitational waves from this epoch, inflation remains the most powerful idea we have for those first moments. It describes a universe that transformed from a quantum speck into a macroscopic cosmos in an instant, setting the entire stage for the cosmic story that followed. What kind of energy could possibly drive such a fantastically violent event? And what does it reveal about the fundamental forces of nature when they were all unified as one? For centuries, the question of other worlds was pure poetry, a dream of distant suns with their own families of planets. That dream became a catalogue in 1995 with the discovery of a world called 51 Pegasi b. This was not a planet in some strange, alien star system. It orbited a star remarkably like our own Sun, but the planet itself was a monster, a Jupiter-sized giant hugging its star so closely that its year lasted only 4 Earth days. Its existence broke all our models, proving that solar systems could form in ways we had never imagined. The floodgates were open. Space telescopes like Kepler and TESS began a relentless census, staring at patches of sky, watching for the telltale, repeated dimming of a star as an orbiting planet crossed its face. They have since confirmed thousands of worlds, and the statistics are clear. Planets are not rare, they are the cosmic norm. On average, every star you see in the night sky likely hosts at least one world. Our galaxy alone could be filled with billions, even trillions of planets. The sheer diversity is breathtaking. We have found searing hot Jupiters with years shorter than a single Earth day, and puffy, low-density worlds that would float in a bathtub if one could be built large enough. We have discovered super-Earths, rocky planets larger than our own, and mini-Neptunes, a class of world that doesn't even exist in our solar system. Most profoundly, we have identified planets orbiting within the Goldilocks zone, that narrow, temperate band around a star where the temperature is just right for liquid water to pool on a planet's surface. The question of life in the universe has been utterly transformed. It is no longer a matter of philosophical wonder, but a practical, data-driven investigation. We are no longer asking if other Earths exist. We are trying to determine how common they are, and which of these distant points of light holds the most promise. The cosmic real estate for potential biology has expanded beyond our wildest dreams. With so many worlds, the silence of the cosmos begins to feel strangely loud. Is anyone else out there looking back into the darkness and wondering the same thing? To find out, we had to learn how to listen. The signal arrived with a rhythm so precise it seemed artificial. In 1967, a young graduate student named Jocelyn Bell Burnell was reviewing data from a radio telescope she had helped build when she noticed a curious bit of scruff on the chart paper. It was a pulse, a sharp burst of radio waves that reappeared every 1.337 seconds with the unerring regularity of a cosmic metronome. The signal was so unnervingly perfect that she and her colleagues half-jokingly labeled it LGM1 for Little Green Men. It was a moment of high drama, the tantalizing possibility of a first contact with an intelligent civilization. The truth, however, was far more extraordinary. What she had found was not aliens but the first known pulsar, a celestial lighthouse of staggering power. A pulsar is the grim remnant of a massive star's death. When such a star goes supernova, its core collapses under its own immense gravity. The force is so overwhelming that protons and electrons are crushed together, fusing into neutrons. The result is a neutron star, an object so incredibly dense that a single sugar cube of its material would weigh billions of tons here on Earth. This city-sized sphere spins at a frantic pace, and its intense magnetic fields funnel radiation into narrow beams shooting out from its magnetic poles. If the star's spin axis is misaligned with its magnetic axis, these beams sweep across the cosmos like the beacon of a lighthouse. From our perspective, each rotation produces a pulse of radiation, a flash we detect with our telescopes. The discovery was a monumental breakthrough. It provided the first direct evidence that neutron stars, which had been theorized for decades, actually existed. These objects are nature's most perfect clocks, with some pulsars spinning hundreds of times per second and maintaining a stability that rivals our best atomic clocks on Earth. This incredible precision has made them invaluable tools for testing the universe itself. By carefully timing the pulses from a pair of pulsars orbiting each other, astronomers have been able to confirm predictions of Einstein's general relativity with stunning accuracy, observing how their orbits decay as they radiate energy away in the form of gravitational waves. In fact, this was the first ever indirect detection of those ripples in space-time. Pulsars are a profound paradox, the tombstones of dead stars that have become essential guides for the living. They are the ultimate symbols of cosmic transformation, where total destruction gives birth to a tool of unparalleled precision. If a single neutron star represents matter pushed to its absolute limit, what universe-shattering event occurs when two of these incredible objects spiral together and collide? Einstein's equations hummed with a prediction so subtle most thought it would never be proven. He theorized that cataclysmic events could send ripples across the fabric of space-time itself. These gravitational waves would be like sound waves traveling through the air, but instead of moving air molecules, they would stretch and squeeze space itself as they passed by. The effect, however, was infinitesimally small. Einstein himself doubted we would ever have instruments sensitive enough to detect such a faint whisper from the cosmos. For a century, these ripples remained a beautiful but unproven idea. Then, on September 14, 2015, everything changed. The twin observatories of LIGO, located thousands of miles apart in Louisiana and Washington, registered a signal. It was not a long, drawn-out hum, but a distinct chirp, a rising frequency that ended in a final, violent shudder. The pattern was unmistakable. It was the sound of two black holes, each about 30 times the mass of our Sun, spiraling toward each other in a final, frantic dance over 1 billion light-years away. In their last fraction of a second, they merged into a single, more massive black hole, converting a portion of their combined mass into pure energy that radiated outward as gravitational waves. The signal exactly matched the predictions of general relativity. We were no longer just looking at the universe, we had learned to hear it. This new sense is profoundly different from sight. Light can be blocked, absorbed, or scattered by dust and gas. Gravitational waves, born from gravity itself, pass through matter almost completely unimpeded. They allow us to perceive cosmic events that are completely dark to telescopes, like the collision of two black holes that emit no light at all. It is like living in a world where you could only see thunderclouds, and then suddenly being given the ability to hear the thunderclap itself. Since that first detection, LIGO and its European counterpart, Virgo, have listened to dozens of these cosmic crashes, not just of black holes but also of neutron stars. In one spectacular event, we both heard the gravitational wave chirp and saw the flash of light from the collision of two neutron stars. A multi-messenger observation that confirmed these violent events are the cosmic forges where heavy elements like gold and platinum are created. This new window on the universe lets us test gravity in its most extreme regime and listen for echoes from the very dawn of time, from moments like the inflationary Big Bang, when the universe itself may have rang like a bell. What other silent, invisible dramas have been playing out in the dark, waiting only for us to learn how to listen? The Hubble Space Telescope turned its gaze toward a patch of sky so utterly dark it was considered a cosmic void. For 10 long days in 1995, it collected every single photon it could, staring into what was thought to be nothing. The result was not an empty black frame. It was a universe in a flashbulb's burst. The Hubble Deep Field image revealed a staggering sight, a tapestry of 3,000 galaxies, each a faint, fuzzy swirl containing billions of stars. All of this cosmic grandeur was crammed into a speck of sky no larger than a grain of sand held at arm's length. This was not just a photograph, it was a core sample drilled deep into time and space. Because light takes time to travel, we were not seeing these galaxies as they are now, but as they were billions of years ago in their youth. Here were galactic toddlers, chaotic and misshapen, caught in the act of formation through violent collisions and mergers. The image was a direct, visceral punch to our sense of place. It proved that the universe is not merely large, it is saturated with islands of stars. Every single point of darkness in our night sky, if we had the patience to look, contains a similar universe of galaxies. We had gone from a single city to a sprawling country, and now we saw that the country was filled with neighborhoods stretching to the horizon in every direction. But this incredible view of individual galaxies also hinted at a larger, invisible architecture. How were all these brilliant islands connected across the immense voids of space? The Hubble Deep Field showed us a universe teeming with galaxies, but it was like looking at individual trees without seeing the shape of the forest. When astronomers began plotting the locations of millions of galaxies, a breathtaking pattern emerged from the chaos. The universe is not a random splatter of stars, but a vast, intricate architecture known as the cosmic web. The Sloan Digital Sky Survey and other massive sky scans have painstakingly mapped this structure, revealing a universe laced with brilliant filaments of galaxy clusters, stretching across billions of light years like strands of a spider's web. These luminous threads connect at dense nodes where thousands of galaxies swarm together in massive clusters, and between them lie the cosmic voids, unimaginably vast deserts of near emptiness that can span hundreds of millions of light years. This is the adult universe, the final form of the tiny quantum ripples we see in the cosmic microwave background. For nearly 14 billion years, gravity has been the great sculptor, patiently pulling the dark matter skeleton and its attached ordinary matter into this magnificent web-like pattern. We are not just living in a galaxy. Our Milky Way resides within a specific filament, part of the local group, which itself is a tiny speck on the outskirts of the immense Laniakea supercluster, a gravitational metropolis containing over 100,000 galaxies. This grand map is the ultimate expression of structure emerging from initial chaos, a cosmic metropolis whose streets and neighborhoods are defined by the invisible hand of dark matter, and whose expansion is being accelerated by the mysterious push of dark energy. We now have a street map of the observable universe, but where exactly is our home address on this map, and how do we know we have it right? Our ability to map the cosmic web, to know our humble address within the Laniakea supercluster, rests entirely on a single, ingenious invention, the cosmic distance ladder. This is not a single tool, but an interlocking series of methods, each one carefully calibrated by the one before it, that allows us to climb from our own backyard to the very edge of the visible universe. The first rung is the most direct. We can bounce radar signals off nearby planets like Venus and Mars, precisely timing how long it takes for the echo to return. This gives us an exact measurement in kilometers of distances within our own solar system. With this solid foundation, we can take the next step outward to the nearest stars, using a technique as old as human vision itself, parallax. Hold your finger in front of your face and close one eye, then switch eyes. Your finger appears to jump back and forth against the background. Astronomers do the same thing with the stars. They observe a nearby star from opposite sides of Earth's orbit around the Sun, a baseline of about 300 million kilometers. The tiny shift in the star's position against the more distant background allows us to triangulate its distance with extraordinary precision. This method, however, only works for a few thousand of our very closest stellar neighbors. Beyond that, the shift is too small to measure, so we need a new kind of rung on the ladder, a cosmic lighthouse whose true brightness we know. This is where Cepheid variable stars, those pulsating beacons that Hubble used, become essential. By measuring the period of their pulse, we learn their intrinsic wattage. Comparing that known wattage to their apparent dimness from Earth tells us their distance. This single step was the key that unlocked the scale of our galaxy and proved that Andromeda was a separate island universe. But even Cepheids fade from view at immense distances. For the farthest reaches, we need the most powerful standard candle of all, a Type 1, a supernova. These are the thermonuclear explosions of white dwarf stars, and they all reach nearly the same peak brightness, outshining entire galaxies for a few weeks. When we spot one of these brilliant flashes in a distant galaxy, we know its true luminosity. Its incredible faintness then becomes a direct measure of its mind-boggling distance. This is the method that revealed the accelerating expansion of the universe, driven by dark energy. Each rung of this ladder is essential, each one supporting the next. Without radar ranging, we could not calibrate parallax. Without parallax, we could not trust the Cepheids. Without Cepheids, we could not calibrate the supernova. This chain of inference turned the sky from a beautiful but flat painting into a breathtakingly deep, three-dimensional map. It gave the cosmos a scale, revealing its true, almost incomprehensible grandeur. Every time we state a number like a galaxy is 13 billion light-years away, it is a testament to this century-long project of human ingenuity. But how solid is this ladder we have built? Our entire cosmic distance scale, and therefore our understanding of the universe's expansion rate, now faces a puzzling tension as measurements from different rungs begin to disagree, hinting that a fundamental piece of our cosmic model might be missing or misunderstood. Our entire cosmic map, built rung by rung, points toward a single, profound moment of origin. By carefully measuring the expansion rate of the universe and the cosmic densities of matter and dark energy, we can run the film backward in time, calculating the moment when everything was condensed into that initial hot singularity. The answer we arrive at is a number of almost unimaginable scale. The universe is approximately 13.8 billion years old. This is not a wild guess. It is a robust conclusion, cross-checked by entirely different clocks. We can measure the ages of the oldest stars in our galaxy by studying the nuclear fuel they have burned, and they consistently point to an age just shy of that 13.8 billion year mark. The cosmic microwave background provides another independent timestamp, its detailed pattern revealing the exact moment when the universe became transparent. All of these cosmic chronometers agree. This number, 13.8 billion years, gives us the ultimate timeline. It frames the entire cosmic story, from the violent flash of inflation and the forging of the first elements, through the dark ages and the ignition of the first stars, to the gradual assembly of galaxies like our own. Our own solar system is a relative newcomer, forming only about 4.6 billion years ago from the recycled debris of long-dead stars. If we compress the entire history of the cosmos into a single calendar year, with the Big Bang at the stroke of midnight on January 1st, then every recorded human event, every empire and every discovery occurs in the last few seconds before midnight on December 31st. We are a fleeting whisper in a cosmic conversation that has been ongoing for eons. This finite framework transforms our perspective, giving a definite beginning to the grand narrative and forcing us to confront our place within it. On a timeline so vast, what unique confluence of events allowed a tiny, rocky world to become a haven for life? That search for other Earths found its most powerful guiding principle not in a telescope, but in a simple, relatable idea. The habitable zone, often called the Goldilocks zone, is the orbital sweet spot around a star where the temperature is just right for liquid water to pool on a planet's surface. Not too close where water would boil away into a perpetual steam bath, and not too far where it would freeze solid into a permanent ice ball. This concept transformed the hunt for life from a blind search into a targeted investigation. Suddenly, with thousands of exoplanets being discovered, we had a practical filter, a way to sort through the cosmic catalog and ask which of these distant worlds might possess that most fundamental ingredient for biology as we know it. But location is only the first clue. The real breakthrough came when we learned to read the air on these distant worlds. Using a technique called spectroscopy, astronomers can analyze the faint starlight that filters through a planet's atmosphere during its orbit. Each gas in that alien air leaves a unique fingerprint, a specific pattern of dark lines in the spectrum of light. We can now scan these atmospheric barcodes from light years away, searching for the chemical whispers of a living world. The most tantalizing biosignature would be a mixture of gases that should not coexist for long without something, perhaps life, constantly replenishing them. On Earth, oxygen is highly reactive, quickly bonding with rocks and other elements. Methane is also readily destroyed in the atmosphere. Finding both oxygen and methane together in an exoplanet's air would be a powerful, though not definitive, hint that biological processes are actively at work to maintain that unstable balance. This has moved astrobiology from the realm of pure speculation into a rigorous, data-driven science. We are no longer just dreaming of life elsewhere. We are building the tools to systematically look for its signatures. And the diversity of planets we have found forces us to expand our imagination. A habitable world might not be a perfect twin of Earth. It could be a moon orbiting a gas giant, warmed by tidal forces rather than sunlight, or a planet tidally locked to its star with a permanent dayside and a permanent nightside. The sheer number of possibilities makes the silence of the cosmos feel increasingly strange. With so many real estate options, from super-Earths to water worlds, the fundamental question shifts. We are no longer asking if life is possible elsewhere, but how common it is for a planet to cross the threshold from a barren rock to a living world. What is the spark that turns chemistry into biology? The next discovery suggests the raw ingredients for that spark are not just common, they are a fundamental part of the cosmic recipe. The silence of deep space is not truly silent. It hums with a faint chemical symphony. Through the ears of radio telescopes, astronomers have listened in on giant molecular clouds, the cosmic nurseries where new stars and planets are born, and they have found them teeming with a rich inventory of complex organic molecules. These are not just simple gases, but the very building blocks of life itself. Amino acids, the Lego bricks of proteins, sugars, and even alcohols have been identified floating in the immense voids between the stars. In a stunning confirmation, the Rosetta spacecraft directly detected the amino acid glycine in the wispy atmosphere, or coma, of comet 67P, Churyumov-Gerasimenko. This was a delivery note from the dawn of our solar system. The profound implication is that the chemical precursors for life are not a rare, earthly invention. They are formed naturally by the complex chemistry of interstellar space, and then distributed throughout young planetary systems by comets and meteorites, seeding new worlds with life's potential ingredients. The universe appears to be pre-loaded with the starter kit for biology. This cosmic abundance suggests that the leap from non-life to life is not a miracle requiring impossible odds, but a process that the cosmos is constantly, quietly trying to initiate wherever the conditions are right. The great mystery is no longer where the ingredients came from, but what cosmic kitchen, what special environment, provided the heat and the stir to mix them into the first living cell. The boiling, acidic waters of a volcanic spring seem like a recipe for sterilization, not a cradle for life. Yet that is exactly where we find entire ecosystems thriving, in conditions that would instantly destroy most living things. These are the extremophiles, organisms that do not merely survive in environments we consider hellish, they flourish. They cluster around superheated vents at the bottom of the ocean, under pressures that would crush a submarine, drawing energy not from the sun but from the Earth's own chemical heart. They have been found buried deep within Antarctic ice, in rocks miles underground, and even swimming happily in the cooling pools of nuclear reactors, bathed in radiation that would be lethal to us. Life, it turns out, is not a delicate flame that needs perfect conditions to survive. It is a tenacious weed capable of pushing through the cracks in reality itself, exploiting any niche, no matter how unforgiving. This radical expansion of life's domain here on Earth has profound consequences for our search beyond it. Suddenly, the frozen, cracked surface of Jupiter's moon Europa is not a dead world but a lid. Beneath its icy crust, a global ocean of liquid water is thought to churn, warmed by the tidal forces of Jupiter's immense gravity. The geysers of water vapor erupting from Saturn's moon Enceladus are not just beautiful plumes, they are invitations promising a subsurface sea that could be sampled simply by flying a spacecraft through them. Even the dry, dusty riverbeds of Mars hint at a past, and perhaps a present where microbial life could persist deep underground, sheltered from the harsh radiation on the surface. The discovery of Extremophiles has fundamentally rewritten our search parameters. We are no longer looking only for planets that are Earth-like, orbiting squarely in the Goldilocks zone. We are now searching for worlds that are Earth-capable, places where life could find a way, even if that way is in total darkness, under a shell of ice, or deep within a radioactive rock. If life can emerge and cling to existence in the most punishing corners of our own planet, then the number of potential addresses for biology in the cosmos has exploded. The universe may be filled with life, not as we know it, but as we are only just beginning to understand it. Our cosmic address has expanded from a single city to an entire continent, but the journey of discovery does not end at the edge of our observable universe. The deepest laws of physics themselves hint at a reality even more immense and strange, the Multiverse Hypothesis. This idea emerges naturally from our most successful theories. The same cosmic inflation that smoothed our infant cosmos could be a perpetual, endless process. When a tiny patch of space-time inflates to become a universe like ours, what about the space-time right next to it? The math suggests that inflation could be creating new universe bubbles constantly, a vast, frothing cosmic foam where each bubble is a separate universe with its own unique properties. String theory, an attempt to unify all forces, adds another layer, predicting a colossal landscape of possible physical laws, with each universe randomly landing on one set of rules. In this staggering vision, our universe is not the universe. It is just one page in an infinite cosmic library. Some of these volumes would be blank, universes that expanded too fast for stars to ever form, or where the forces were too weak for atoms to hold together. Others might be filled with wild physics we can scarcely imagine, where gravity is repulsive or time runs backward. Our own universe, with its seemingly perfect constants that allow for galaxies, planets, and life, would then lose its special status. The profound fine-tuning we observe, the precise strength of gravity and the nuclear forces, might not be a designed miracle, but a simple coincidence. We exist because in an infinite array of possibilities, a universe with our rules had to appear somewhere. This is the ultimate Copernican revolution, demoting not just our planet or our sun, but our entire cosmos from a unique creation to one possible outcome in a meta-reality beyond our reach. Are we just one bubble in an endless, frothing sea? The idea is currently untestable, a philosophical frontier more than a proven fact. Yet it represents the final, logical extension of our cosmic perspective, a humbling suggestion that all we have ever known and ever will know might be just a single flicker in an ocean of eternal darkness. This fine-tuning of the cosmos is so precise it feels like a mathematical whisper. The strength of gravity, the charge of an electron, the force that binds atomic nuclei, all of these fundamental constants are dialed to such exact values that even a tiny change would render the universe sterile. If gravity were slightly stronger, stars would burn through their fuel in a fleeting million years, collapsing before life could ever emerge. If the nuclear force were a fraction weaker, hydrogen would never fuse, and the cosmos would be a dark, starless expanse of primordial gas. The universe appears to be rigged for life. This observation is the heart of the Anthropic Principle, a concept that bridges the cold equations of physics with the warm fact of our own existence. The weak Anthropic Principle offers a straightforward, almost tautological explanation. We observe a universe with these specific properties for one simple reason: we are here to do the observing. In a cosmos with different, incompatible constants, there would be no one to wonder about them. It is like a lottery winner marveling at their luck. The odds were astronomically against them, but someone had to win. The strong Anthropic Principle takes a more provocative stance, suggesting the universe in some sense must have laws that permit the development of conscious life. This is not an explanation, but a profound puzzle. Why is the cosmos so bio-friendly? Is our existence the result of unimaginably good fortune, a single winning ticket in a cosmic lottery? Or is it a statistical inevitability, as the multiverse idea suggests, where every possible set of physical laws plays out in an infinite number of parallel realities, and we simply find ourselves in one of the rare habitable ones? This principle forces a conversation between science and philosophy, placing the observer back into the cosmic story after centuries of being sidelined. It suggests that our ability to measure, to question, and to ponder the heavens is not a minor side effect of cosmic evolution, but a fundamental feature woven into the fabric of reality itself. The universe became aware of itself through us. This final discovery ties our fleeting, conscious moment directly to the most fundamental parameters of existence, leaving us with the ultimate question: are we a random accident in a cold, indifferent void, or is the very nature of the cosmos somehow leaning toward the creation of life and mind? Our journey through these 25 discoveries reveals a single, powerful story: the relentless unseating of humanity from the center of everything. Each breakthrough was a lesson in humility, a cosmic correction to our self-importance. We learned we do not reside on a stationary stage at the heart of creation, but on a tiny, spinning rock orbiting a common star. That star is just one among hundreds of billions in a galaxy that is itself a mere speck in an ocean of galaxies. We discovered our entire universe is not eternal and static, but had a fiery beginning and is flying apart at an ever-increasing rate, driven by a mysterious dark energy we cannot comprehend. The very substance of reality is dominated by ghosts, by dark matter we cannot see and dark energy we cannot grasp, while all the stars and galaxies we cherish amount to less than 5% of the whole. Yet, in this vast and seemingly indifferent cosmos, we also found a profound connection. The iron in our blood was forged in the heart of a long-dead star. The very atoms of our bodies are borrowed starlight, on loan from the cosmic cycle of life and death. The chemical ingredients for life itself are scattered like seeds across the galaxy, waiting for the right conditions to sprout. This is the true legacy of science, not a cold list of facts, but an epic story of exploration and wonder. It is a narrative that constantly refines our self-perception, teaching us that we are not the center of the universe, but we are a way for the cosmos to know itself. Our story is not over. What new chapter will we write when the next great discovery, perhaps of life beyond Earth, forces us to once again redefine our place in the grand scheme of things? From a perfect crystal dome centered on Earth to a universe of dark energy and invisible matter, this journey of 25 discoveries has done far more than fill textbooks. It has systematically dismantled our cosmic address and rebuilt our identity from the ground up. Each revelation, from the heliocentric solar system to the accelerating expansion of everything, was a lesson in profound humility. We are not the center of creation. We live on a fleeting speck orbiting an ordinary star in a quiet suburb of a galaxy that is itself one of countless trillions, adrift in a cosmos dominated by forces we cannot see. This could feel like a narrative of insignificance, a cold demotion into obscurity, but it is also a story of breathtaking empowerment. It is the story of a species that, from this tiny vantage point, has managed to decode the laws of the universe, to hear the echoes of its birth, and to trace our own elemental origins back to the hearts of long-dead stars. The astronomer Carl Sagan captured this paradox perfectly when he reflected that we are a way for the cosmos to know itself. Our consciousness is the universe becoming aware of its own grandeur and its own mysteries. So the next time you stand under a dark sky, remember that you are not just looking out at the void. You are the universe looking back at itself, pondering its own origins and its ultimate fate. This story is not over. What will the 26th great discovery be? Will it be the detection of life on a distant world, or the final unraveling of dark energy's secret? Share what you believe will transform our view next in the comments. Subscribe for more journeys into the unknown, and always keep looking.